Hello everyone, this is Physics 103. This lesson is on atomic structure, and today we are going to talk about many electron atoms. So, from the previous lectures, we have already successfully solved the wave function for the hydrogen atom, and also we have known the associated quantum numbers that is described in the solution to the wave function. So the hydrogen atom is just a one proton and one electron. So when we talk about many electron atoms, of course it has many protons and many electrons, just like the other elements in the periodic table. So, of course, we are also interested in knowing the wave function and the quantum numbers that we will use for these other atoms. But turns out that this isn't a simple task, and solving the hydrogen atom itself is already a hard task. So how do we even approach many electron atoms? So first, let us briefly recap what happens in a hydrogen atom. So you have a positively charged nucleus and a cloud of negatively charged electrons. So this is already described by the wave function, but what about for other elements? So for example, this is hydrogen. What about if we want to know the wave function for helium? So let's add here another proton, and of course there will be another electron in the cloud. So what do we know now here? So helium has now changed its nuclear charge to 2e. So moreover, for element X, its nuclear charge will be Ze, where Z is the number of protons. So for our atom with Z protons, its energy, we may say, we can modify the energy to be minus 4 pi epsilon naught squared. The mass of the nucleus, I'll call that, this is N, so this should be nucleus. This shouldn't be mass of the nucleus, this should be mass of our electron, or our particle that we are interested in. In this case, it's an electron. So mass of the electron times Z E squared times the charge of our electron. So E squared over 2n squared h bar squared. So what is new here is that for adding up a charge on the nucleus will add up a Z term in our energy levels. So this only considers a sort of single electron in the energy here. But in reality, there are actually multiple electrons that are present inside a nucleus with a higher charge. So for example, you have more protons in the nucleus. Of course, there are also neutrons. But for simplicity's sake, we have a high number of Z. So that would correspond to a lot of electrons. So when you have a lot of electrons inside an atom, these electrons will cause a repulsion to each other. So what this will do is it will mess up the whole wave function. So as we approach a higher atomic number in our elements, this approximation in energy becomes less and less accurate. So this is one failure of trying to bring the solution of the hydrogen atom for many electron atoms, but this is one way of approaching it. So the next approach is the central field approximation. So this resolves the problem of having many electrons interacting with each other, or interacting electrically with each other. So what is the central field approximation? So take our zth element before. So for example, madami siyang, it has many protons, many neutrons, and it will have, of course, many electrons too. So what this central field approximation does is it will take away all the electrons here, and it will treat the central or the nucleus as if these electrons are, how do you say, are balancing out its whole charge. So the electrons are balancing out. So you can think of it as these electrons being squished out inside the nucleus, and this will turn out to be the same nucleus with a single electron left outside the nucleus. So what are the results of this simplification? So first is the nucleus, or sorry, the potential, if you would recall in our Schrödinger equation, will be changed. depending on how many electrons are being squished into the nucleus. Second is that we are left with a single electron. So when we are left with a single electron, this solves the problem of many electrons repelling each other. So this is the central field approximation. Again, this is a very poor approximation too, because if you come to think about it, all these electrons are being squished into into the nucleus as if they were just some source of a charge. So, but nevertheless, if we have a single electron left outside our nucleus, if we have a one electron left, we can now solve the Schrödinger equation only with a different potential associated with it. Okay, so upon solving the Schrödinger equation, we can have the same set of quantum numbers, so n, l, ml, and ms for a single electron. Okay, so this will have also a problem if we try to compress the electrons in just one state. So all these electrons are compressed sort of in a single state. So in the next videos, we will try to resolve that problem.